Okay, let's start today by addressing the elephant in the server room. We have this serious addiction in the world of artificial
Oh,
intelligence.
we absolutely do.
We are entirely addicted to compute. I mean, we treat processing power like it's just this infinite resource, and the prevailing logic for the last few years has been incredibly simple. If you want a smarter model, you just build a bigger model.
Right.
You throw more data at it, you double the parameters, and you just burn enough electricity to power a small city.
It is the classic bigger is better dogma.
Yeah.
And to be fair, it has worked. That is honestly part of the problem. It works so well. You look at GPT models or PaulM or any of the recent massive architectures, and the industry sort of just stopped asking if there was a smarter or more elegant way to do it. We kind of just kept buying more GPUs.
Right, until you hit a wall. Or I guess more likely until you're a researcher at a university or a startup founder or just a student listening to this, and you realize you don't actually have a spare $10 million to train a model. You're effectively locked out of the cutting edge because the entry fee is a literal supercomputer.
Which is exactly why the paper we are covering today in this deep dive is such a breath of fresh air. It really challenges that whole brute force mentality.
Yeah, I was so excited to dig into this one. The paper is titled ELECTRA Pre-Training Text Encoders as Discriminators Rather Than Generators. And it's a collaboration between Stanford University and Google Brain led by Kevin Clark alongside Minthang Lung Kwok Viola and Christopher D. Manning.
A very heavy-hitting team.
Very. And the mission for this deep dive is to figure out how this team managed to build a high-performing AI model without needing those massive energy-sucking compute resources we usually associate with big tech. Specifically, how they built something that outperformed the massive GPT models of that era using a fraction of the resources.
And when we say a fraction, we really aren't talking about shaving off 10% or something. We're talking about a model trained on a single GPU.
A single GPU, like literally one card.
One NVIDIA V100 GPU running for just about 4 days.
That is just wild to me. Usually when we read these deep learning papers, the hardware section reads like a shopping list for a massive data center.
Right. It's pages of infrastructure.
Yeah, but this has a real David versus Goliath energy to it. One GPU beating models that took massive clusters weeks to churn through.
It really does. But I think to understand how they pulled off this efficiency heist, we first have to look at the battlefield. We need to define the status quo they were actually fighting against.
Okay, so set the scene for us. Before Electra, what was the heavyweight champion in this space?
Well, at the time this paper dropped, the landscape was entirely dominated by BERT.
Right, BERT. Bidirectional encoder representations from transformers. That was the model that really changed everything for natural language processing.
Exactly. And BERT popularized a specific training method called masked language modeling, or MLM for short. If you want to understand why ELECTRA is such a leap forward, you have to first understand the massive inefficiency built into MLM.
Let's break that down then. How does masked language modeling actually work in practice?
Okay, so imagine I give you a sentence. Let's say, the quick brown fox jumps over the lazy dog. In MLM, the system randomly takes a virtual Sharpie and blacks out, or masks, about 15% of those words.
So maybe the word fox just becomes a blank bracket, a mask token.
Exactly. It becomes a special mask token. And the model's only job is to look at the surrounding context and guess the specific word behind that mask.
Which on the surface seems like a solid way to learn. Like if I see the quick brown blank jumps, I have to understand the relationships between the words to know that fox fits there and, I don't know, refrigerator doesn't fit.
It works beautifully for accuracy. It's essentially a fill-in-the-blank test, and it forces the model to learn context from both the left and the right sides of the sentence.
Right.
But think about the math of the actual computation. To make that one guess, the model still has to process every single word in the sentence. It'd have to build a rich mathematical representation for the and for quick, and for brown, and for jumps, and so on.
Okay, so it is doing the heavy lifting for the whole sentence.
It is doing the computational work for 100% of the tokens. But here is the kicker. At the very end of the pass, when it calculates the loss, which is the error signal that actually teaches the model and updates its weights, it only looks at the 15% you masked.
Wait, really? So it reads the entire book, thinks about every single word, but the teacher only grades 3 sentences.
Precisely. It literally ignores the other 85% of its own predictions. It calculates them, but it throws them away because there was no mask there to solve.
That sounds incredibly wasteful.
It is a massive waste of floating point operations. You are spending compute to process unmasked tokens, but the model receives no direct learning signal about them whatsoever. To get a high-quality model using this method, you have to run this process millions and millions of times just to compensate for that weak, sparse learning signal.
It's basically like trying to learn a new language by only filling in crossword puzzles rather than just reading the actual articles. You'd have to do a ton of crosswords to get fluent.
That is a perfect analogy. You're learning, but so slowly. And there is a secondary problem the authors highlight in the introduction, which they call the mismatch problem.
The mismatch, what does that mean?
Well, think about the training data. The model sees this special artificial mask token everywhere during training. It learns to rely on it. It gets really good at staring at that specific artificial symbol and figuring out what it's hiding.
Right, because it's in 15% of the training data.
Exactly. But then when you actually use the model in the real world, say you fine-tune it to classify a news article or answer a customer service question, do those mask tokens ever appear?
Oh, I see. No. Real life doesn't come with fill-in-the-blank underscores.
Right, so the network is practicing on data that looks fundamentally different from the data it actually sees during deployment. It creates a discrepancy between how the model practices and how it's expected to perform. ELECTRA was designed specifically to solve both of these issues in one go, the 85% compute waste and that training mismatch.
Okay, so let's unpack the solution. The paper proposes something they call replaced token detection. How is that different from just guessing the missing word?
It changes the fundamental nature of the task. Instead of masking a word and asking, what is the hidden word, ELECTRA replaces words with plausible fakes and asks, is this word real or is it an imposter?
Okay, but where do the fakes come from? You can't just swap in random words, right? Like if I change the chef cooked the meal to the chef bicycle, the meal that's way too easy, the model wouldn't learn anything deep because the grammar is obviously broken.
Correct. If the fakes are obvious, the learning signal is basically zero. The model just learns to spot basic syntax errors. So to make this work, ELECTRA actually uses two neural networks working in tandem. This is the core architectural innovation here. You have a generator and a discriminator.
Now hold on. A generator and a discriminator fighting it out. This sounds suspiciously like a GAN. You know, generative adversarial network. We see those in image generation all the time, making deepfakes in art. Is ELECTRA just a GAN for text?
It quacks like a duck, and it looks like a duck, but it really doesn't swim like one. The authors do admit it is GAN-style learning, but there are crucial technical differences. But before we get into the nuance of why it's not a standard GAN, let's just look at the actual workflow.
Okay, walk us through the two-network process.
First, you have the generator. This is a small, lightweight network, typically just a small masked language model. Its only job is to do the old-school task. Take the sentence with the masks and fill them in with plausible alternatives.
So the generator is doing the inefficient MLM work, but because it's small, it's cheap to run.
Exactly. So let's use the example from Figure 2 in the paper. It takes the input, the chef masked the meal, and it fills it with something plausible. Let's say it guesses the word ate. So the generated sentence becomes, the chef ate the meal.
Which makes total sense. Ate is grammatically correct and fits the context.
It fits perfectly. But the original source word was cooked. Now, the second network, the discriminator, which is the actual main ELECTRA model we care about, takes that completed sentence.
Yeah.
The chef ate the meal, and its job is to look at every single word in that sentence and classify it.
Okay.
So it looks at the chef, it says real. It looks at chef and says real. It looks at ate.
And it has to spot that it's a replacement, so it flags it as fake.
Exactly. And then it looks at the ate and it says real and meal and says real.
I see the efficiency gain immediately. In the old BERT way, we only learned from the one masked word. The other words were ignored. In this new way, the discriminator's making a prediction and getting graded for every single word in the sequence.
That is the big aha moment of the paper. The discriminator has to evaluate 100% of the tokens. The learning signal is incredibly dense compared to MLM. This effectively multiplies the value of every single training step because the model learns so much faster when it's constantly being corrected on everything it sees, not just a 15% sample.
But I want to push on that fake label for a second. In the example you gave, the chef ate the meal is a perfectly valid English sentence. If the discriminator learns that ate is a fake word in that context, isn't it learning something technically wrong? Like, isn't it learning that chefs don't eat?
That is a really sharp observation, and it gets right to the heart of what ELECTRA is actually learning. It isn't learning truth in some broad philosophical sense. It is strictly learning distribution.
Distribution.
Yes, it is learning that in this specific context, based on the exact original source text, I am trying to mimic the word 8 was not the token that actually appeared.
So it's strictly checking identity against the original document.
Yes, but think about what is required for the model to successfully make that distinction. To know that 8 is a replacement and not the original cooked in a complex, nuanced paragraph,
Yeah.
the model has to develop an incredible grasp of semantics, tone, and flow.
Right. It forces the model to learn the subtle nuances of language to tell the difference, rather than just spotting obvious syntax errors. It has to be a highly observant critic.
Exactly. And it turns out being a critic is a profoundly efficient way to learn language structure.
So let's loop back to that Jan comparison. You mentioned it sounds like a generative adversarial network, but it isn't quite one. Why the distinction? We have a faker and a detective fighting it out. Why does the paper go out of its way in the methods section to say this isn't adversarial?
There are three main reasons, and they're a bit technical, but very important for why this actually works so well. First, in a traditional GAN, the generator is trained adversarially. That means the generator is actively trying to trick the discriminator. It gets a mathematical reward when the discriminator makes a mistake.
Right, so in again, it's I fooled the cop, so I win.
Exactly. But in ELECTRA, the generator is trained with maximum likelihood. It is just trying to guess the right word to fill the blank based on the context. It isn't trying to be evil or deceptive. It's actually trying to be accurate. It's not optimized to fool the discriminator at all.
So it's not a battle. It's more like the generator is a slightly incompetent assistant trying their absolute best to reconstruct the document, and the discriminator is the editor checking their work.
That's a great way to put it. Now, the second difference is about what happens when the generator is actually correct. In an image GAN, if the generator produces an image from scratch, that image is fake by definition because the AI made it.
Okay.
But in ELECTRA, what happens if the original word was cooked and the generator happens to guess the word cooked?
Well, it guessed the right word. It matched reality.
Yes. In a GAN-NAN, that would still be a generated sample and therefore fake. But in ELECTRA, the discriminator is explicitly taught to label that correctly guessed word as real.
Oh, wow. So even if the AI generated the word, if it matches the original truth, we teach the discriminator to treat it as the truth.
Exactly. We care about the identity of the data, not its provenance. But the third and probably biggest reason it's not a standard GAN is the problem of discreteness in text.
Discreteness. Break that down for us.
Sure. In an image GAN, you're dealing with pixels. Pixels have continuous numerical values. You can slightly shift a pixel from a value of, say, 200 to 201 to make it look just a tiny bit more real. You can use calculus, specifically gradients, to guide that shift smoothly.
Right. You can gently nudge a pixel's color.
But you cannot nudge a word. Text is discrete. You can't slightly shift the word cat to be more like the word dog. It's either cat or it's dog. There is no cat-dog halfway point in the vocabulary.
So the generator can't get feedback saying you were almost right, just slide the word a little to the left?
Exactly. This makes back-propagating the error, meaning sending the correction signal back from the discriminator to the generator, practically impossible in the standard GAN way. You cannot differentiate through a discrete sample.
So how do they fix that?
ELECTRA bypasses that whole mathematical nightmare by simply disconnecting the two training loops. The generator trains entirely on its own task of filling the blank, and the discriminator trains on its own task of spotting the replacement. They work together, but they aren't locked in that standard adversarial death spiral.
That sounds so much more stable. Okay, so we have this clever two-network system, a cooperative generator and a super dense learning discriminator. Let's talk about the scoreboard. Does this actually work better, or is it just a really elegant theory?
Oh, the results are undeniable. They use the GLUE benchmark, which stands for General Language Understanding Evaluation. It's basically the standard report card for these NLP models. And they started by training a model they called ELECTRA Small.
And how small is small in this context?
It uses about 14 million parameters. For context, a standard BERT-based model is roughly 110 million parameters. So ELECTRA Small is about 1/20th the size of something like BERT Large.
Okay, and this is the one you mentioned earlier that was trained on the single gamer GPU.
Yes. One single GPU for 4 days. And on that GLUE benchmark, it scored 5 points higher than a comparably small BERT model. But the real headline stat, the one that really turned heads, was that it outperformed GPT.
We're talking about the OpenAI GPT models.
Yes, specifically the standard GPT model referenced in the benchmarks of that era. ELECTRA Small managed to beat a model that required 30 times more computing power to train.
That is just a ridiculous return on investment. 30 times less compute for better performance.
And essentially proved that you don't actually need massive compute clusters to get smart behavior if your training task is fundamentally efficient.
That is incredible for the small model. But what happens when they scale it up? Like, does the efficiency hold up against the heavyweights of the time?
It definitely does. They also trained ELECTRA large. And that model performed comparably to Roberta and XLNet, which were the absolute state-of-the-art heavyweights at the time.
Okay, so it matched them.
It matched them, but here's the efficiency kicker. It achieved that parity while using less than 1/4 of the computing power those other models required.
Less than a quarter. So that's essentially a 75% discount on your massive data center training bill.
Exactly. And when they decided to let it train longer, an experiment they called ELECTRA 1.75M steps, it actually outscored Roberta and XLNet on the GLUE and SQUAD benchmarks. So it's not just more efficient, it's strictly learning better per clock cycle.
I want to dig into the why behind that. We have the high-level concept that replaced token detection is just denser learning. But there are some really interesting details in the technical deep dive of the paper, specifically the ablation section, where they intentionally break parts of the model to see what makes it tick.
Oh, the ablations are fascinating here. They really reveal the special sauce of the architecture. One key finding they highlight is about weight sharing.
That's where the generator and the discriminator share their internal dictionary, right?
Yes, exactly. Specifically, they share the token embeddings. Imagine the generator's learning what the word apple means, and the discriminator is also independently learning what apple means. If you keep their brains separate, they both have to do all that basic vocabulary work from scratch.
Which is redundant.
Very. But by tying the embeddings together, when the generator learns that apple's a fruit, the discriminator instantly gets that knowledge too. The generator updates the shared embeddings really densely because it's generating words, and the discriminator benefits from that foundation.
So it prevents the discriminator from having to waste time learning basic vocabulary. It can just focus all its energy on the higher-level detective work.
Exactly. But there is an even weirder finding in Figure 3 regarding the size of the generator. You would naturally assume that to train the best possible discriminator, you would want the best possible generator. Like if you want to train a Sherlock Holmes, you need a Moriarty.
Yeah, that makes total sense. Iron sharpens iron. If the generator is dumb, the discriminator has it too easy and gets lazy.
Right. But the data showed something completely counterintuitive. They found the system actually works best when the generator is significantly smaller than the discriminator, typically about 1/4 to 1/2 the size.
Wait, why? If the generator is weak, isn't the fake spotting task just too easy?
If it's too weak, yes, the task is too easy and learning stalls.
Yeah.
But if the generator is too strong, if it becomes as big and smart as the discriminator, it effectively solves the problem. It generates replacement words that are so perfect, so contextually flawless and indistinguishable from the original text that the discriminator literally cannot tell the difference.
Ah, I get it. If the counterfeit bill is atom for atom identical to the real bill, the detective isn't learning anything. They're just guessing randomly.
Exactly. The error rate goes up to 50-50, the learning gradient becomes entirely noisy, and the whole system stalls out. So a Goldilocks zone exists. You need a generator that is good enough to be plausible and tricky, but not so good that it's perfect.
That is such a cool nuance. It implies that for AI learning, the difficulty of the curriculum has to be incredibly carefully managed. A test that is too hard is just as useless as a test that is too easy.
There's one more experiment in the ablations I found really telling. The researchers actually anticipated a specific criticism from the community. They asked the question, is ELECTRA winning just because it looks at every token?
Right, like, is it the fake detection task itself that matters, or is it literally just the mathematical fact that we are calculating loss on 100% of the words? Maybe if we just forced BERT to predict every single word, it would be just as good.
Right. So to test this, they built a stepping stone model called All Tokens MLM. They took standard BERT, but modified it to predict every single word in the sentence based on context using some clever masking tricks so it couldn't just copy the input directly.
So they effectively leveled the playing field regarding the sheer volume of the learning signal.
Exactly. Both models now look at 100% of the tokens. And the result was really interesting. All Tokens MLM was definitely better than standard BERT. So yes, looking at all tokens helps a lot. But ELECTRA still beat All Tokens MLM significantly.
Oh, wow. So the discriminative task itself, the actual real versus fake judgment, is inherently more educational than the generative predict the word task.
That seems to be the definitive conclusion. Distinguishing valid data from high-quality noise forces the model to learn sharper, more robust boundaries in its understanding of language. It's just a richer, denser signal.
Which brings us to the bigger picture here. I mean, this paper came out a few years ago, which in AI time is basically the Jurassic period. But the legacy of ELECTRA seems incredibly relevant right now as we are collectively hitting these massive compute walls.
Absolutely. We are seeing a huge resurgence of interest in sample efficiency right now. You have things like small language models becoming a massive topic for running AI locally on phones or laptops. The core principles of ELECTRA, figuring out how to get more signal out of less data, are absolutely crucial for that future.
It also speaks directly to that democratization we mentioned at the very start of the show. If you need a cluster of 1,000 GPUs to do anything useful, then AI is just the exclusive domain of 3 or 4 tech giants. But if you can do meaningful, high-level pre-training on a single GPU, suddenly universities, startups, and independent researchers are fully back in the game.
And that is incredibly healthy for the entire field. We really don't want the definition of intelligence to be dictated solely by who has the biggest electricity bill. Innovation almost always comes from constraints, and ELECTRA is just a masterclass in innovation under constraint.
I want to leave everyone listening with a final thought about the cognitive side of all this. We usually associate intelligence with creation, the genius artist, the brilliant writer, the generator. But this paper suggests that the critic might actually be the smarter one.
It is a really provocative idea.
If the discriminator learns faster and deeper than the generator, does that imply that critical thinking, the ability to look at something and discern its truth or its realness, is a higher order function than pure generation?
I think it heavily suggests that you cannot have good generation without excellent discrimination. You need that internal critic to edit your own thoughts. Maybe that is what these modern large language models are essentially doing behind the scenes. They're developing a highly refined sense of what sounds right before they even output a single word.
So if you want to write a better novel, maybe spend a little less time typing and a lot more time editing.
Or at the very least, learn to tell the difference between a plausible cliche and a genuine insight. That is essentially the ELECTRA way.
We will wrap it up right there. This has been a really fun deep dive into ELECTRA. If you want to see the charts for yourself, especially that Goldilocks curve for the generator size we talked about, definitely check the show notes for the link to the original paper.
It is absolutely worth a read for the technical details alone.
Thanks for joining us for this deep dive. And until next time, keep your discriminators sharp.